All right, video number 2 for the week. We're going to introduce stability in cloud development as the slide says, and this will be the bulk of our lecture for the upcoming week. And so again, I really more than normal encourage you to look through these, and I'll make that clear in the email, not that I didn't already in class on Wednesday. And so what we're going to start here with is going to be built upon throughout the next couple of lectures. And in some ways, this is some of my favorite material to teach. It seems difficult at first, but it kind of all comes together really cleanly at the end. And so I'm going to bring up a number of comments that I'm going to kind of want you to put an asterisk next to. The things that if you can remember are going to help you a lot as we move forward. And the first is in this first motivating point. Warm air rises, cold air sinks. And we've already broken this down. The idea that warm air is less dense, and things that are less dense are going to rise. It's why humans can float more easily in the oceans where it's salty. That more dense water allows the less dense human to float. And so warm air that's less dense is going to rise above that cold air. We talked about this with frontal boundaries, and we're going to start with that basic premise and work our way into why thunderstorms happen. We're going to talk about what stable air is versus what is unstable air. And we've kind of, again, at least touched upon this, but now we're going to really dig into what that means and how it relates to precipitation as well as thunderstorms. And we're going to throw out some new terms. We're going to bring up things such as lapse rates. How is the temperature of the atmosphere changing as you go up with height, as we work into some really crazy terms like conditional instability and other aspects that will be useful to help us assess whether the environment is supportive of thunderstorms on any given day. And so the general premise is that clouds are going to form as air becomes lifted and the air cools. And so we're really going to work with this section stability to determine whether or not that air that becomes lifted, something like a front or some daytime heating or other type of boundary, something again that we've discussed already that lifts the air upward against its will at times. It may be to where we have a cold front moving in and that air in front of the cold front doesn't want to budge, but that even colder air coming in behind forces the air upward. And stability is going to help us understand whether or not we may end up getting some stratus layered clouds or whether we might get some deep cumulus and cumulonimbus clouds that can create thunderstorms and severe weather. And so looking at stability, we have, let's just go ahead and put it all up there to start this slide. The idea of atmospheric stability, and what we're going to talk about here is the idea of parcel theory. We're going to make a parcel. Think of a beach ball or a volleyball. Something bigger than a baseball, something smaller than, that didn't come together well. Think of a beach ball or a volleyball. And the idea that we're going to move this parcel around, and we're going to talk about how it can expand and contract, but for right now we can look at this red ball. And the idea that if I had someone go down into this trough or pit and push that red ball up the side and then stop forcing it up the side, it would simply return down to the bottom. Sure, it might swing down a couple of times, but it would eventually come back to rest where it's sitting right now. This is what stable air is going to do. It's going to want to return to its original position unless we're forcing it with something like a front. Neutral is the idea of a displaced parcel will move if it's forced to a different location, but it's not going to do any more than that. And so if someone else were to go push that red ball from left to right across the screen in this middle image and stop right here, the ball would stay there. It wouldn't return, but it also wouldn't continue to move. We're going to find that the atmosphere is not normally in a neutral state. It's usually going to be stable or unstable, and usually layers of both at any given time. In reality, the unstable environment is what, well, it's kind of interesting. Here, any one of you could give this little red ball a nudge in either direction, and that initial acceleration is going to cause it to continue to accelerate away from its original position. And so if you push a little bit to the left, it's going to roll down this hill and simply just keep going without any additional force acting on it. It's not going to return to its original position. It's not going to stop unless we have something stopping that acceleration. And so these are going to be the three terms that we use quite often, and we'll build on these over time. What we'll find as we move forward, so this is a bit of a tease, is that the atmosphere is usually in what's known as a conditionally unstable or conditionally unstable environment. And you see in the blue box, you'll see the term conditionally stable and conditionally unstable, especially if you're reading your textbook. These are interchangeable terms. It's just conditioned on certain things that, again, we'll get into a little more detail here. But in the red ball scenario here, to be able to get to this point of being unstable, the bottom schematic in the last slide, we would need some type of forcing to overcome this initial stable portion. In other words, someone would need to give it enough force to make it all the way up to the top of the hill and allow the ball to come down the side of the hill. It's conditional upon this forcing occurring to get to the top and to be able to come down the side. And so when we work with stability, we're first going to work with the idea of parcel theory. Parcel theory is what I was trying to come up with, the idea of a beach ball, something that can expand and contract, size of a beach ball, basketball, volleyball, whatever your desirable size is. And I'm going to pause this slide for a moment. All right, folks, apologies for that. Something I had to jump away from the computer about. So we're talking about our air parcel, this basically small pocket of air that's allowed to expand and contract. So it has balloon here, and the idea that within this air parcel we have constant mass. There's a certain number of molecules that we're not going to increase or decrease, even though this parcel can change size. So it always triggers me out. The volume can change, and so we can make this larger, we can make it smaller, and since there's a fixed number of molecules, the density can change. If we make it smaller, it's going to become more dense. If we make it bigger, it's going to become less dense, and that is going to have an impact on temperature. And so we're going to talk a little bit about how quickly all the molecules are moving. And this is going to be one of those other things that we bring in as kind of our core principles here as we work our way through stability. And so our air parcel is, for lack of a better term, allowed to rise and sink. This is going to depend on the situation. Think back to the stuff that we talked about earlier. Warm air rises, cold air sinks. And that really is the basis for whether or not this parcel is going to rise or sink. Let me start that over. Importantly, though, what's going on inside this parcel is independent of what's going on around the parcel, or what we refer to as the environment or surrounding environment. And so that's going to be one of the things that we have to be sure we're keeping separate, what's going on in the parcel and what's going on in the surrounding environment. And so certain rules are going to be established for how this parcel warms and cools. The environment's doing whatever the environment's doing. We take measurements like we do with our radiosondes, our weather balloons, to tell what the environment's doing. Then we learn a little bit about what the parcel is actually doing. So in this example, we rise it up from 0 meters up to 1.5 kilometers. We'll see in a little bit that our parcel is going to cool at 10 degrees for every kilometer. So it drops from 25 to 10. It expands in size because as it moves from a lower altitude to a higher altitude, the pressure is lower here. And so if we take something, the idea that this is at a higher pressure and move it up here, that high pressure pushes outward on the boundaries. It's the same principles with pressure gradient force. So that expands, it's going to mean it's less dense, and it's going to mean that it's cooler inside your parcel. Notice though, we didn't necessarily cool the environment at the same rate that we cooled our parcel. And this right here, this comparison that I'm circling on the slide as I say this, is going to be what we really work towards, understanding what happens when the temperature of our parcel and the temperature of environment are different. And so we'll spend a couple more slides and then we'll go ahead and call this a day and get going back at it Monday. This is stuff that is on our next midterm, so we're going to want to make sure we're through it by Wednesday of next week. When we compress air, when we take that parcel and force it inward, it's going to warm the air inside. If you've ever used a bike pump, maybe you like to go for some cycling rides and you take the pump and you inflate the tire and it gets really difficult towards the end, but then if you by any chance feel the the pump, it's warmed up. You're kind of compressing the air, as you see here in A, pushing it into the tire, and that's going to cause the cylinder of your bike pump to warm up. Conversely, if you were to expand air, it's going to cool. That's like what we saw on the last slide. As that air rose and our parcel expanded, the air inside of it became less dense and it cooled. And so, unfortunately, we're not right now in the classroom, but if you were to do this with a demo and some type of a pump, you would notice that it can become pretty warm pretty quickly due to this compression of air. We'll even use terms such as compressional warming. I probably used that term when we were on the last series of slides with local winds, our Chinook winds or our Santa Ana winds. As this wind comes down the terrain, it compresses and it warms. And so we're going to talk about one more term here. Let's call it a day after the slide, but this is an important slide, so fight through the next minute or two here. We're going to talk about air as being either saturated or unsaturated. And so I'm going to put it out there right now as another one of those. Write it down and put an asterisk next to it. If air has 100% relative humidity, if it has a temperature equal to its dew point, or if you really like, it has a vapor pressure equal to its saturation vapor pressure. In other words, it is truly saturated. That's one step. If it has anything other than saturation, it can be muggy outside in summer and have a relative humidity of 90%, that's not saturated. So we are only talking about pure saturated air versus anything else. That's really what you can bin the two things as. 100% relative humidity or the other descriptors and anything else. And so unsaturated air, anything with a relative humidity of less than 100% that is lifted upward, is going to cool at a term that we use here, adiabatically. And we'll get into adiabatically next week. And so here's your last action. Let's get both bits up here. Let's go ahead and write these down. Be ready to attack this on Monday. The idea of the dry adiabatic lapse rate. Write it down once and then use the acronym, the DALR. The DALR is equal to 9.8 degrees Celsius for every kilometer. For the purposes of MET 103, use what's in the parentheses, 10 degrees Celsius per 1,000 meters. It's basically the same. It makes all the math much, much simpler, and it's common to do that if you're not doing technical analysis. And so you may see a lab that kind of asks you a little bit about the different values. You can throw the stuff in there, but anytime we're doing calculations, really focus on this 10 degrees Celsius per 1,000 meters, which we oftentimes call 10 degrees Celsius per kilometer. And so basically, if you do some real simple math, divide both of these by 10, it means that every time you go up 100 meters, you're going to cool things by 1 degree. And so this is what happened a couple slides ago. We went from a temperature of 25 Celsius. We went up a kilometer, cooled it to 15 degrees Celsius. We went up another half a kilometer and cooled it down to 10 degrees Celsius. Another take it to the bank is sinking air is going to warm at the same rate. In fact, sinking air is incredibly simple. Sinking air always warms at this rate. So what I basically teased is the fact that rising air is going to sometimes behave differently. Sinking air is going to always warm, and we'll explain that better as we work through some problems, often that involve terrain, to really help us understand how stability works with rising and sinking air. All right, there is your primer on stability. We will continue with this on Monday. Enjoy the weekend. That should have some pretty nice weather. Take care. Stay healthy.